Oil that waterproofs wood, rust-proofs metal, and seals boats with a single coat, no synthetic additive, for over 1,000 years. Then the companies that sell what replaced it made sure you would never hear about it. A single gallon pressed raw from a seed costs under $2 where the trees still grow. It covers roughly 400 square feet. Once cured, the finish is waterproof, mold-resistant, food-safe, and flexible enough to move with the material beneath it without separating. Ships sealed with this oil crossed the South China Sea in the 12th century. The hulls held. Tools coated with it in Qing Dynasty workshops survived 3 and 4 generations with no reapplication. It worked in 1100, it worked in 1700, it worked in 1943 when the United States classified it as a strategic war material. Today, the coating aisle at any American hardware store carries dozens of petroleum-derived synthetic finishes. The oil that outperformed them for a millennium is either missing from the shelf entirely or buried behind products that cost 10 to 50 times more per square foot. This cuts roughly 40% while keeping every concrete fact and the rhetorical rhythm. The main moves merged the description and cold open into one flowing passage, eliminated the redundant second introduction. There is a finishing oil and trimmed restated qualities already implied by the specifics. And the reason has nothing to do with performance. The oil is called tung oil. It comes from the seed of the tung tree, Vernacea fordii, a deciduous species native to the mountains of southern China. The tree grows to roughly 40 feet. It produces clusters of large, round fruit, each containing 4 to 5 seeds. Those seeds are approximately 35% oil by weight. You crush them, you press them, you collect what comes out. That is the entire manufacturing process. The earliest recorded use of tung oil as a protective finish dates to writings from the Qing Dynasty, around the 10th century, though oral tradition and archaeological evidence suggest it was in use centuries before that. Chinese shipbuilders discovered that raw tung oil, when brushed onto wood and exposed to air, underwent a chemical change. It did not simply sit on the surface the way animal fats or waxes did. It penetrated into the grain, bonded with the cellulose fibers, and then hardened from the inside out into a tough, transparent film. This was not a slow discovery. The applications multiplied quickly. Furniture makers in Hunan and Sichuan provinces used it to seal tables, chairs, and storage chests. Farmers applied it to tool handles and plow blades. Builders brushed it onto structural beams and exterior posts exposed to monsoon rains. Boat builders along the Yangtze and the southern coast used it as the primary hull sealant, often mixed with lime powder to create a waterproof putty called chunam that filled seams between planks. By the Qing Dynasty, tung oil was one of the most widely traded commodities in southern China. The production method had not changed. Trees were planted, seeds were harvested, oil was pressed in simple wooden or stone presses operated by hand or by water wheel. There were no additives, no solvents, no catalysts. The oil came out of the seed ready to use. What made tung oil different from every other plant-based oil available at the time, and there were many, including linseed, walnut, and perilla, was the specific molecular structure of its primary fatty acid. Tung oil is roughly 80% alpha-eliostearic acid, a conjugated trianoic fatty acid with 3 double bonds, arranged in a pattern that makes the molecule extraordinarily reactive when exposed to oxygen. In plain language, tung oil wants to harden. It does so faster, more completely, and more durably than any other natural drying oil. When raw tung oil is applied to a surface and left exposed to air, oxygen molecules attack those conjugated double bonds and trigger a process called autoxidation. The fatty acid chains begin to cross-link, bonding sideways to each other, forming a dense, 3-dimensional polymer network. This is not evaporation. The oil does not dry by losing moisture. It cures by building a new molecular structure within the wood or on the metal surface. The result is a finish that is chemically distinct from the liquid that was applied. It is harder. It is insoluble in water. It resists acids, alkalis, and alcohols. It does not soften in heat the way petroleum-based polyurethane can. The cross-linking density of cured tung oil is higher than that of cured linseed oil by a significant margin. Linseed oil's primary fatty acid, alpha-linolenic acid, has 3 double bonds as well, but they are not conjugated. They are separated by methylene groups, which means the cross-linking proceeds more slowly, less completely, and produces a softer, less water-resistant film. This is measurable. Tung oil films reach full hardness in 3 to 5 days under normal conditions. Linseed oil films can take weeks and still remain slightly tacky. Tung oil films show less than 2% water absorption after 24 hours of immersion. Linseed oil films absorb significantly more. This is why Chinese shipbuilders chose Tung oil over every alternative available to them. A hull sealed with Tung oil could sit in salt water for years. A hull sealed with linseed oil could not. The proof was not confined to China. When Tung oil first reached European markets in the late 19th century, industrial chemists tested it immediately. They found what the Chinese had known for centuries. In 1869, samples of Tung oil were analyzed in France and found to produce films of unusual hardness and water resistance. By the 1890s, British and German paint manufacturers were importing it in bulk for use in marine varnishes, floor finishes, and industrial coatings. The United States entered the Tung oil market in the early 20th century. American paint companies, including the predecessors of what would become Sherwin-Williams and Pittsburgh Plate Glass, recognized that Tung oil produced a superior finish for outdoor applications. Demand grew so quickly that the U.S. Department of Agriculture launched a federal Tung oil program in 1905, importing seeds and planting experimental orchards across the Gulf Coast states. Mississippi, Louisiana, Alabama, and Florida had climates warm enough to support the trees. By the 1920s, the American tung industry was producing millions of pounds of oil annually. The USDA published bulletins praising its performance. Mississippi alone had over 100,000 acres of tung orchards by the late 1930s. Then came the test that mattered most. During World War II, the U.S. military classified tung oil as a critical strategic material. It was used to seal ammunition crates, coat electrical insulation, waterproof canvas, and protect metal surfaces on vehicles and weapons exposed to tropical humidity in the Pacific Theater. The War Production Board controlled its allocation. It was rationed. It was stockpiled. The military treated it the way it treated rubber and aluminum, as a material essential to the war effort that could not be adequately replaced. The performance data from wartime use was unambiguous. Tung oil coatings outperformed synthetic alternatives in humidity resistance, adhesion, and flexibility under temperature extremes. Metal tools and weapons coated with Tung oil-based finishes showed measurably less corrosion than those coated with the alkyd resins that were beginning to emerge from the petrochemical industry. The U.S. military knew what it had, and then the war ended. What happened to Tung oil after 1945 is not a story about failure. It is a story about economics, patents, and the rise of an industry that needed Tung oil to disappear. During the war, American chemical companies, DuPont, Dow, Union Carbide, Monsanto, had invested massively in petrochemical infrastructure. They had built plants to produce synthetic rubber, synthetic resins, synthetic solvents. When military demand dropped, those plants needed civilian markets. The coatings industry was an obvious target. Petroleum-derived alkyd resins could be manufactured at scale from cheap crude oil feedstocks. They could be formulated into paints and varnishes that dried faster than raw tung oil, though not harder. They could be mixed with volatile solvents that made application easier for unskilled consumers. Most importantly, they could be patented. Every new formulation, every new additive package, every new resin blend was a proprietary product with protected margins. Tung oil could not be patented. It was a seed oil. It came out of a tree. Any farmer could grow the tree, any press could extract the oil, and any person with a brush could apply it. There was no intellectual property to protect, no formulation to license, no additive package to upsell. For the petrochemical industry, tung oil was not a competitor. It was a category problem. It proved that a natural, unmodifiable, freely reproducible substance could outperform the products they were trying to sell. The displacement did not happen through a single act. It happened through a series of market shifts that, taken together, made tung oil economically invisible. First, the petrochemical companies invested heavily in advertising. By the 1950s, Paint advertisements in American magazines and on television promoted the ease, speed, and modernity of synthetic finishes. Polyurethane was marketed as the future. Tung oil was not mentioned. It was not attacked. It was simply absent from the conversation. Second, retail distribution shifted. Hardware stores and lumber yards began stocking the products that paint company salesmen promoted. Shelf space went to cans of polyurethane, alkyd varnish, and latex paint, all petroleum-derived, all carrying higher profit margins for the retailer than a jug of raw oil. Third, and most consequentially, the American tung orchards were destroyed, not by policy, by weather and economics. A series of severe freezes in the late 1950s and early 1960s killed millions of tung trees across the Gulf Coast. The 1958 freeze alone devastated orchards in Mississippi and Louisiana. Replanting would have taken 7 to 10 years before new trees reached full production. By that time, synthetic coatings had captured the market. Farmers converted their land to soybeans and timber. The USDA tung program was quietly defunded. By 1970, domestic American tung oil production had effectively ceased. China remained the world's dominant producer, but American imports declined steadily as the coatings industry reformulated its products around petroleum chemistry. The supply chain that had once moved tung oil from Chinese presses to American shelves was allowed to atrophy, not because the oil had changed, because the industry around it had. Today, if you search for tung oil in an American hardware store, what you will most likely find is a product labeled tung oil finish that contains little or no actual tung oil. This is legal. The Federal Trade Commission has not enforced labeling standards that would require products marketed as tung oil to contain a minimum percentage of the real substance. Many products sold under the tung oil name are blends of petroleum distillates, mineral spirits, and synthetic resins with trace amounts of tung oil added for marketing purposes. The real product, raw, pure, 100% tung oil pressed from Vernicia fortii seeds, is available, but you have to look for it. Specialty woodworking suppliers carry it. A quart costs between $25 and $40 in the United States. A gallon runs $70 to $120. These prices reflect import costs, small batch distribution, and the fact that the domestic supply chain no longer exists. In rural China, the same gallon costs the equivalent of $1 to $3 US. The performance gap between tung oil and its synthetic replacements has not closed. Modern testing confirms what wartime data showed decades ago. A 2015 study published in Progress in Organic Coatings compared tung oil-based films to commercial polyurethane coatings across 7 performance metrics: hardness, adhesion, flexibility, water resistance, chemical resistance, UV stability, and VOC emissions. Tung oil matched or exceeded polyurethane in 5 of the 7 categories. It was inferior only in drying speed and initial surface hardness, both of which are consumer convenience metrics, not durability metrics. In the categories that determine how long a finish lasts and how well it protects the substrate, tung oil won. A 2018 study at the Forest Products Laboratory, a USDA research facility in Madison, Wisconsin, tested tung oil as a wood preservative for outdoor applications. Pine samples coated with raw tung oil and exposed to accelerated weathering showed 60% less moisture uptake than uncoated controls and significantly less surface degradation than samples coated with commercial deck sealers. The researchers noted that tung oil's ability to penetrate below the surface rather than forming a film on top gave it a structural advantage. When surface films crack, water enters. When a penetrating finish is present throughout the wood fiber, there is no single point of failure. In metalworking, the data is equally clear. Tung oil has been used as a rust-preventive coating on hand tools, blades, and cast iron surfaces for centuries. Modern corrosion testing, salt spray exposure per ASTM B117, shows that a properly cured tung oil film delays the onset of visible rust on carbon steel by 200 to 400 hours, depending on film thickness. This is comparable to many commercial rust inhibitors that cost significantly more and contain petroleum solvents classified as hazardous air pollutants under the Clean Air Act. The environmental comparison is not subtle. Tung oil contains 0 volatile organic compounds in its raw form. It is non-toxic. It is biodegradable. It is food safe. The FDA lists it as an approved substance for food contact surfaces. A finish made from tung oil releases nothing into the air during application or curing. A finish made from polyurethane releases diisocionates during application and continues to off-gas formaldehyde and other VOCs for weeks or months after curing. The EPA classifies several common polyurethane components as probable human carcinogens. One product is pressed from a seed and has protected surfaces for 1,000 years. The other is synthesized from crude oil, releases toxic compounds, and was invented to generate patent revenue. The building codes do not distinguish between them. The market treats the synthetic as the standard and the natural product as the specialty alternative. In countries where the petrochemical industry did not rewrite the coatings market, tung oil never left. In Vietnam, tung oil is still used as the primary wood and metal finish in rural construction. In parts of Yunnan and Guizhou provinces in China, families press their own oil from trees growing on their own land and apply it to everything from kitchen tables to roof beams to iron cookware. The cost is the labor of harvesting. The material is free. In Paraguay, which has extensive tung tree plantations originally established in the mid-20th century, tung oil is exported as an industrial coating for use in marine, automotive, and flooring applications across South America. Paraguayan producers market it as a high-performance, non-toxic alternative to petroleum finishes, the same claim the USDA made in the 1930s. In New Zealand, small-scale furniture makers and boat builders have adopted tung oil as part of a broader movement toward non-toxic finishes. Several New Zealand-based companies now sell pure tung oil for residential and commercial use, marketing it on the same properties Chinese craftsmen identified a millennium ago: penetration, hardness, water resistance, and longevity. You open a tin of it, the smell is faint, nutty, vegetal, nothing like the chemical sharpness of a synthetic finish. You brush it onto a piece of raw walnut. The oil soaks in immediately. It does not pool. It does not bead. It pulls itself into the grain the way water enters dry soil. Within a minute, the wood changes. The figure deepens, the color warms. Grain patterns that were invisible on the raw surface emerge, as if someone turned on a light behind the wood. You wipe the excess. You wait. Over the next 24 hours, the oil begins to cure. The surface loses its wet feel. It becomes smooth, then firm, then hard. After 3 days, you press your thumbnail into the surface. It does not dent. You set a glass of water on it. The next morning, you lift the glass. No ring, no white mark, no swelling. You run your hand across the finished surface. It does not feel like plastic. It does not feel like lacquer. It feels like wood, but wood that has been made permanent. The pores are sealed, but they are not filled. The texture is still there. The material is still breathing, still expanding and contracting with humidity and temperature, but the oil has locked out the moisture and the oxygen that cause decay. The wood beneath this finish will look the same in 20 years, in 50, in 100, if the historical record holds. This is what 1,000-year-old technology feels like under your hand. The question is not whether tung oil works. The wartime data proved it. The USDA data proved it. The Forest Products Laboratory data proved it. 1,000 years of Chinese shipbuilding proved it. The question is why, in a market that claims to value performance, durability, and safety, a proven, non-toxic, renewable finish was replaced by a toxic, petroleum-derived, patent-protected one, and why the replacement is still treated as the default. The answer is not complicated. It is economic. A gallon of raw tung oil applied by hand with no proprietary equipment, no licensed applicator, and no repeat purchase necessary generates almost no profit for anyone other than the person who grows the tree. A gallon of polyurethane sold in a branded can, reformulated every few years to justify a new SKU, applied with proprietary tools, and requiring reapplication every 3 to 5 years, generates profit at every stage of its life cycle for the chemical company, the retailer, the applicator, and the recoating contractor. The finish that lasts is a problem for everyone who sells the finish that does not. Tung oil is not illegal. It is not banned. It is simply absent, removed from supply chains, excluded from professional training, unlisted in specification guides, and buried under marketing budgets it cannot match. The physics has not changed. The chemistry has not changed. The performance data has not changed. The only thing that changed is who profits. There is a material that insulates a wall to R40 using nothing but agricultural waste and a hand press. It costs less than fiberglass. It contains no formaldehyde. It does not burn. It was tested by a national laboratory and classified as superior to every commercial insulation product on the market. Then the industry that sells fiberglass funded the committee that wrote the code that requires a material with a certification the agricultural product was never allowed to apply for. That video is on your screen right now.